So 4.3 logarithmic functions. I don't know if y'all remember back to last year, hardy har har, when we were studying exponentials, right? Exponentials grow very rapidly. The more you have, the more you gain. Remember that? Yeah. Well, the log function, which is what logarithmic functions are kind of called, you can abbreviate them log functions. They follow up usually on the study of exponential functions because they are the inverses of exponential. These are the inverses of exponential. So what would that mean? If something exponential grows rapidly because the more you have, the more you gain, then if something grows logarithmically and it's the inverse, what would you expect it to do? Yeah, it would grow at a decreasing rate. It grows slowly. Okay. So what logs were invented to do is to slow down growth. Okay. Logs are invented. They were invented to slow down huge growth. So they were an invention of man. It was a notation that first started by the mathematician John Napier. I believe he was Scottish, maybe John Napier, and he had this idea of if you're working with really large numbers, like you got to imagine back in the day, people were looking up to the skies, and when you look up to the skies, you see the stars and you see the planets, right? And the distances between those are very great. Yes, very great. You also have people looking under microscopes at the time where the numbers are really small, like 0.00000. So what Napier said is, hey, if we're looking at these really astronomically large numbers or these microscopically small numbers, we can kind of bring them up to kind of this level playing field, if you will, and we can start looking at the exponent on this as the size of that number as a relative representative of the number. Okay, so when you're talking about the distance between planets, they might all be measured in like tens of thousands of miles, right? So you might think of that, okay, tens of thousands of miles, that would be like 10 to the 6th or 10 to the 7th or 10 to the 8th. We can write them all as a power of 10, and then we can start looking at the exponents, 7, 8, 9, 10, as the representative of the number, okay? So that's the idea. They started out as what they were called Napier's bones, and you can look on the left-hand side there. That's kind of a depiction of what Napier's bones look like. They were little wooden sticks, and they had little logarithmic numbers. I don't even know how to use them. Maybe some rainy day. I didn't even get motivated over Christmas to learn how to use Napier's bones. But what they did is they kind of helped you calculate, much like log tables or a slide rule back in the day used to do. Now, if you look on the right-hand side, you also have Napier's bones. That's what Napier looks like without his skin. So you got Napier's bones on the left, and you got Napier's bones on the right. Are either one of them scary? No, the answer is no, okay? I don't want you to be scared of logs, okay? Most math students, when we get to logs, they develop a very negative connotation of logs. They hate logs, they don't like logs, they're scared of logs. If they see a log, they cringe. It's kind of like a word problem. I don't want you to be scared of logs at all, okay? Unless you're scared of these or you're scared of this, and this is just a cartoon depiction of his bones. That's not really his bones, in case you were wondering, right? Don't be scared. Okay. So what is a log exactly? What is a log exactly? We're going to abbreviate logarithm log. Are you all okay with that? So when I say what is a log, that means basically what is a logarithm? We use log as a represent logarithm. What is a log? Okay, here it is. A log is simply an exponent. Reread. A log is simply an exponent. What is a log? An exponent. What's another word for exponent? A log. Are you afraid of exponents?
No.
No. So are you going to be afraid of logs?
No.
No, you are not. You are not going to be afraid of logs. Now, the log is a particular exponent. That's what makes it different than just a random exponent. It is a particular exponent. Here's what it is. It is the unique exponent to which you must raise a particular base, like base 10 or base 5 or base e, to achieve a particular result. For example, I say 2 to the 4th equals 16. Would you agree with that? 2 to the 4th is equal to 16. That's a mathematical sentence. It's true. And of course, on this side, that means 2 times 2 times 2 times 2. Just to review what the exponent means. The exponent means that we have 4 factors of the base. We call 2 the base. We have 4 of them, and when you multiply 4 2's together, you get 16. So we can actually turn this mathematical sentence on its head and talk about what this is in terms of a log. If the log is the exponent, what must be the log? What's the exponent in this problem? 4. Okay, so 4 is the log. 4 is the log, we say, base 2. 4 is the log base 2. Okay? That means that when you take the base 2 and you raise it to the 4th powered, you get your desired result of 16. Okay? Now here's how we would write this. We would write it like this. We say log base 2 of 16 is 4. Let's write that out. Log base 2, this is how we read it. Base 2 of 16 is 4. So the base, which is an exponential, becomes the base of the log, but we write it as a subscript. Okay? Log base 2 of 16 equals 4. And now what we have is we have 2 sentences right here. This sentence and this sentence right here, mathematically, they mean the exact same thing. So like in your English class, you have prepositional phrases. You can put them in different parts of the sentences, and it doesn't change the meaning of the sentence, right? For instance, when I get home, comma, I do my homework. Everyone understands that? When I get home, comma, I do my homework. I can flip that around and say, I do my homework when I get home. Is that really the same sentence? The sentence structure is just switched, but the meaning is still preserved. That's kind of what we have going on here. We have 2 mathematical sentences with the verb is, that's the equal sign, and they mean the exact same thing. So if 2 to the 4th equals 16, it's because log base 2 of 16 is 4. Or if log base 2 of 16 is 4, it's because 2 to the 4th is 16. So what you need to get in the habit of is when you see something like this, not to be scared, right? Not to be scared, but to realize what the log is. Okay? The log, the log, let's highlight this. Let's go over our definition here. The log, the log, the log is 4. You see that? The log equals 4. The log is 4. What's the log? 4. What's the exponent over here? 4. The log is 4, right? But when we write it like this, we put the base down at the bottom here. So the reason we can read log base 2 of 16, we could say 2 to what power is 16. That's how you can read this. 2 to what power is our result 16? 4. Okay? This 16 is called the argument. The 16 is called the argument. It's the, let's see if I'm still recording. It's our desired result. It's our desired result. 2 to what power is 16? 2 to the 4th power is 16. Okay? So let's kind of talk about how we can go back and forth between these two. Okay? We say that the exponential function and the log functions, as I already mentioned, are inverses of each other. So let's go back to our exponential function. If f of x is equal to b to the x, this is exponential. Remember, b is the base, x is the exponent. If the base is bigger than 1, it's growth. If it's between 0 and 1, it's decay. Y'all remember that? Okay. We'll say that the inverse, remember we denote the inverse like this. F to the negative first power. We say that's the inverse of f. It undoes the work of f. It's going to be your log function, and we write it like this. We write that as log base b of x. So notice what's common in both of these. The b and the b are both called the base. Let me pick purple here. The b is the base in both forms. Okay, so if you were to graph these, and let me show you what this looks like, because I think we've talked about the natural log of x, haven't we? ln of x as a parent function. If you have this graph right here, this could be y equals b to the x. Its inverse is going to look like this. This is y inverse, which equals log base b of x. And what other features do we have here? Remember, the exponential function has a horizontal asymptote on the x-axis, and the log function has a vertical asymptote on the y-axis. Do these two inverse graphs have any symmetry of each other? You remember the symmetry for inverses? Yeah, what is it across? They're reflections across what line? Origin. Not the origin, but if you imagine this line running right through the middle here, does it appear that those are reflections of each other across that line? Yeah, that's the magical mirror. That's y equals x, if you recall. Okay? So we had e to the x as our parent function, and its inverse was the natural log of x. The natural log of x is just log base e. So if I had y equals 4 to the x, what would the inverse function be? What would the equation of the inverse function be? Log base 4 of x is how we read that. Yeah. Log base 4 of x. You need to make sure you're reading it correctly. Log base 4 of x. So 4 to the x, which could be the blue one up there, it's growth. And then log base 4 of x. That could be the red graph right there. It's logarithmic growth. So notice what I said about how logs slow down the growth. For the exponential, look in yellow here. As we go to the right, it's increasing at an increasing rate. See that? Increasing. Whoa, I hate writing with a highlighter. That's the first time I've done it this year. I was doing so well. Increasing at an increasing rate. Increasing at an increasing rate. Whereas what happens when you come down here and you look at the red? As you go out to the right, is it still increasing? Yeah. It's still increasing, but it's tapering off. It's curving downward almost, right? So this is increasing at a what rate? Yeah. Increasing at at a decreasing rate. So the log function looks almost like it's leveling out. It almost looks like there's a horizontal asymptote there because it's flattening out so dramatically. It looks like it's got a horizontal asymptote, but it doesn't. It actually goes to infinity. It goes up forever and ever and ever, just increasingly more slowly. Okay? It slows down the growth. All right? So exponentials and logs are related how? How are they related to each other? But what do we call them? Oh, inverse. They're inverses. They're inverses of each other, right? Logs are inverses of exponential. Logs are inverses of exponential. They undo the work. Now, what is a log in its most basic sense? It is an exponent, right? A log is an exponent. Now, as I mentioned, there is a way to have the same sentence structure to go back and forth between the two. So for lack of a better name, I call this the conversion formula. Okay? The conversion formula. It's an if and only if statement. Remember this double arrow right here, which goes both ways, means if and only if. IFF, we usually say. So that means you could start on either side and say if then. So let's start on the left side and read it. If log base b of x equals y, then b to the y must equal x. That's what it says. But it works the other way around as well. If you start on the right-hand side, if b to the y equals x, then log base b of x equals y. One of them implies the other. They are actually equal to each other. What we need to be adept at is going back and forth between the two, okay? Back and forth between the two. There's an easy way to go from a log to an exponential. Some people call it the around the world. You start with the base and you go around the world like this. So b raised to the yth power equals x. B to the yth power equals x. B to the yth power equals x. But I want to show you a better way to do it, okay? This will basically reinforce the idea that these are inverses of each other. What happens if you compose two inverses back to back? What if you have f of f inverse of x? Remember that from last semester? If you compose two inverses back to back, what should happen to them? They should cancel each other out, right? And you should end right back where you started. Everyone agree? So if I start with x and I apply f inverse, which could be 2 steps to the left, and then I apply f, which undoes it 2 steps to the right, I'm back where I started at x. Remember that? And does the order matter? 2 left and 2 right, or 2 right and 2 left? Am I back where I started? Does the order matter? No. So remember, this is the only time that composition is commutative. It's the only time composition is commutative, when you're composing two inverses back to back. So here's what we could do. If we start with log base b of x equaling y, here's what we can do. We can actually do what's called exponentiate both sides. Here's what that would look like. It would be b to the log base b of x equaling b to the y. So what did I essentially do? I just put the base b on both sides, and I left the left side be the new exponent, and I let the right side be the new exponent. See that? Now, what should happen on the left side? Yeah, so the left side should turn into what? 1. Not 1, but x, right? X. Because b to the log base b of x is just x, based upon what we have above here, right? Start with x, log it base b, and then turn around and exponentiate it base b. You're back where you started with x, yes, yes? Okay, so notice that gets you from the left side to the right side. Log base b of x equals y implies that x equals b to the y. Okay, you could also do it the other way. If you start with b to the y equals x, you can log both sides. Take the log of both sides. So here's what that would look like. That would be log of b to the y equals log, it would be base b, sorry, log base b of b to the y equals log base b of x. So instead of exponentiating both sides, I take the log of both sides. And now the left side is the new argument on the left, and the right side is the new argument on the right. What should happen up here? What is log base b of b to the y? Well, if I start with y in this case, yeah, it should undo each other, right? I should get right back where I started with y. And I get y equals log base b of x. So that's how you can get from the right side to the left. Okay? So we have this right here. We have b to the log base b of x equals x. And we also have log base b of b to the x equals x. When you compose two inverse functions, like b to the x and log base b to the x, back to back in any order, they undo each other, don't they? Okay, cool. Cool, so we've established two real important things here so far. First of all, a log is an exponent. It's a very particular exponent, and the log is also the inverse of a particular exponential function. Everyone good so far? Yeah, yeah. In fact, let me scoot this over so that it's right above there. Now it looks better. You don't have to worry about going around the world now. You can go back and forth from the left to the right or the right to the left in the conversion formula simply by either exponentiating both sides base b or logging both sides base b. Okay? Now, that doesn't mean that I don't want you to try and do some things intuitively. I always want you to keep in mind what a log is. A log is just an exponent to which we must raise a particular base to achieve a desired result, called the argument. So let's look at example 1a. Log base 3 of 27 equals x. It's already solved for x, isn't it? So log base 3 of 27 must be a number. What is log base 3 of 27 equal to? Well, here's your mind. Here's how you can think about it. 3 is the base. So 3 to what power equals 27? 3 to the 9th is 27? 3 to the 3rd. Yeah. 3 to the 3rd power. So x equals 3 since 3 to the 3rd equals 27. Does that make sense? So log base 3 of 27 is the same thing as 3. If you have a Jersey number of 3, you can put log base 3 of 27 on the back, and it's the exact same number, right? That's your number. Because 3 to the 3rd power is 27. Now, if you wanted to, here's the other way you could do it. You could do it kind of algebraically, as we mentioned above. You can actually exponentiate both sides. Here's what that would look like. You would have 3 to the log base 3 of 27 equals 3 to the x. And what happens on the left-hand side? What's 3 to the log base 3 of 27?
That's 3. Wait.
It's 27. Yeah, this is one of the important things that you need to walk away with today. When you exponentiate and you log with the same base back to back, they undo each other, and you're just left with the argument, 27. So we get 27 equals 3 to the x, and now you can probably solve this in your head, right? 3 to what power is 27? You could actually say 3 to the x equals 27 is 3 to the third, and here's like another little property here. When you get the bases the same, when you get the bases the same, you can equate the exponents. If you have 3 to the x equals 3 to the y, that implies that x equals y, because an exponential function is 1 to 1. It passes both the horizontal and the vertical line tests. So x has to equal 3. But you can think about it intuitively as well. Whenever you solve this equation right here, 27 equals 3 to the x, whenever you solve that intuitively, it's the same thing that we did up there when we asked ourselves in the very beginning, 3 to what power is 27? Okay? All right. Is anyone afraid of logs yet? Good. Let's try this out. X is equal to log base 4 of 1 over 64. So again, it's solved for x. We know that this is equal to a number. I just want to simplify this number. Log base 4 of 1 over 64. What is it equal to? Well, I'm just going to write x equals. Let's see. Here's how you think about it. 4 is the base, and x is the log, right? So 4 to what power is 1/64? 1/4?
-4.
Let's see. If you say it's 1/4, let's try it out. That would mean that 4 to the 1/4 power is 1 over 64. Is that true? No, because that would mean the fourth root of 4, right? So that's actually not 1 over 64. Let's see. I need to make it a fraction, so how could I do that? Brady, I think you said something. Yeah, and how about -4? Let's try that out. That would mean 4 to the -4th power is 1 over 64. Now, 4 to the -4th is the same as 1 over 4 to the 4th, right? So that at least gets us in fraction form. But is 4 to the 4th 64?
No, it's 4 to
No, that's 16 squared.
the third.
It should be to the third power, right? X to the -3rd. Because 4 to the third is 16 times 4. These are common cube roots and fifth roots and stuff that you should know. The cube root of 64 is 4, because 4 times 4 times 4 is 64. They'll occur with increasing frequency, so you can get used to them if you're just paying attention. But you should flat out just memorize it. 64 is the perfect cube root. It's 4 to the third power. How do we make it 1 over 64? We say it's to the -3rd power, right? So here's what we could say. The answer is -3 since 4 to the -3rd power is 1 over 64. All right, try this one out. Log base 2 of the square root of 32 equals x. It's already solved for x, so this log base 2 of the square root of 32 must be a number. So here's your mindset, right? 2 to what power of x? X is the log. 2 to what power of x is the square root of 32? 1/4? Let's try it. If it's 1/4, then 2 to the 1/4 equals 32. The square root of 32, is that right? No, that would mean the fourth root of 2, which is not equal to the square root of 32. So it's not a fourth. Here's another way you can go about doing this if it's not easy for you in your head. You can actually take the argument and try to write it as a power of the base. Okay? Use the idea that they're inverses of each other. So x could equal log base b of b to the x, right? We know that from earlier. Log base b of b to the x is just x. So if you ever have an argument like the square root of 32, if you can write it as a power of the base, your answer is just the exponent. So let's see if we can do that. Log base 2 of the square root of 32. Well, first of all, I can get rid of the square root, can I? The square root's going to take it to the what power? 1/2 power. Good. And now 32. Is 32 a power of 2? It's one that you will memorize if you don't get accustomed to it. It is. It's 2 to the what power? 2 to the 6 is 64. It's 2 to the 5th power. If you multiply 2 by itself 5 times, you get 32. All right, everybody, what's 2 to the 5th power? 32. What's the 5th root of 32? 2. Got it? 2 to the 5th power is 32. So if I write it like that, now I got that's equal to x. So now I have log base 2 of 2 to the, what do I do with these two right here? The 5 and the 1/2. Do I multiply or add them? I multiply them and I get 5/2. Okay? Now, watch what I have here. I have log base 2 of 2 to the 5/2 power. So 5/2. Yeah. These right here, essentially, these go away. Because logging base 2 and exponentiating base 2 are inverses of each other. So you get x equals 5/2. Okay? All right. Here's the getting the bases the same. I already said this. Since b to the x and log base b of x are both 1 to 1. Remember what it means to be 1 to 1? They pass both the vertical and the horizontal line test. Okay, and we know that that's true. We can see that from the graphs up here. They both pass the vertical and the horizontal line test. Another method for solving is what I call the get the bases the same method. The get the bases the same, or the GT-BTS method. Okay, get the bases the same method. If you're solving a log equation or evaluating a log, you want to set it equal to x, then if you can get the bases the same, b to the something equals b to the something, then the exponents have to be equal to each other. Then x has to equal y. Okay. Same thing if you have logs. If you have log base b of x equals log base b of y, that means that x has to equal y because they're 1 to 1. So you get the bases the same. Okay. That's what we did right here. 3 to the 3rd equals 27, or right here, actually, right here. 27 equals 3 to the x. We did 3 to the 3rd equals 3 to the x. Therefore, x has to equal 3. All right. Additional fact. The previous fact is in a box, while this fact is not in a box. Memorize that. That's an important fact, isn't it? Yeah. I might quiz you on that fact. That's a pretty good fact. Now, there are two special logarithmic bases that we are going to be looking at. And they're also the two that you're probably the most familiar with. They're the two that your calculator are programmed to work with. Base 10, which is called the common base, or the common logarithmic base. This is basically scientific notation. Scientific notation. If you have an example like 3.1 times 10 to the 5th power. Yeah, that's a big number, right? This is base 10. So this is why Napier invented logs. He says, that's a big number. We don't have to worry about all the zeros. We could just say, hey, let's write all the numbers as a power of 10, and then we could just compare relative sizes by comparing exponents. So 10 to the 5th is going to be smaller than 10 to the 6th, because 5 is less than 6, all right? So if you use scientific notation, you're already accustomed or familiar with base 10. Here's the fact. When you write log base 10 of x, it is so common that we can omit the base, the subscript, and you can just write log of x, okay? So very, very important. If you ever just see log and we say of x, and there's no subscript there to imply what the base is, the implied base is what? 10. If you want the base to be anything other than 10, like base 4 or base 5, you need to write the subscript there, base 4 or base 5. Otherwise, everyone is going to assume that you're talking about base 10. All right. The other base that's very, very important is the natural base, and we're already familiar with that one. The natural base is base e. So when you use base e, you have what's called the natural log instead of the common log, and we're familiar with that already. It looks like this. Log base e of x, we abbreviate ln of x. ln of x. And ln comes from the Latin for logarithmic naturalis, or logarithmus naturalis. We reverse the order, okay? So whenever you see ln of x, that's the same as log base e of x. ln of x is log base e of x. It's the natural base. Okay, that's the one that we use more primarily in this class, whereas base 10 is what you use in your science class primarily. Okay, sometimes base 10 is called the scientific base. All right, here are some properties of common logs. Common logs means base what? Base 10. Okay, here are some facts. What is log of 1? 0, apparently. Should you memorize that?
Yeah.
You should, right? Now, you don't have to flat out memorize it. You can think about it. When I ask you what log of 1 is, what's the implied base there when it's not showing? The implied base is 10. You would say, okay, 10 to what power is 1?
0.
0, right? So we could actually say since 10 to the 0 power equals 1. Right? What's log of 10? 1. And you know what the reason is? Because the implied base 10 to the 1th power is what? 10. Yeah. Let me squeeze another one in here. What would log of 100 be?
That'd be 10 or 2.
2, because that's the same as log base 10 of 10 squared, right? Which is 2. And it's since 10 squared equals 100. What would log of 1,000 be?
3.
3. Get it? See how it works with base 10? It's real easy. You just count the number of zeros. Okay? Count the number of zeros and you got your log. That's just looking at the exponents. So in general, what does that mean? That means log base 10 of 10 to the x is equal to what? X. Okay? And then we can flip it around. 10 to the log base x is also x. This is the fact that these two are what's of each other? Invert. Y equals 10 to the x, and y inverse equals log of x are inverses of each other. So when you compose those in any order, doesn't matter which one you do first, they undo each other, and you're right back where you started. Okay. Let's try an example right here. Let's squeeze one in. What would log of 1 over 100 be? Negative 2. Everyone agree? Negative 2. Yeah. Because 10 to the negative second is 1 over 100. Good. You got the idea. Okay. You could write that as log base 10 of 10 to the negative second. Okay, good. Now, the same exact properties work when we switch bases from base 10 to base e. What is the natural log of 1? 0. And the reason would be since e to the 0 is what? 1. Any non-zero number to the 0 power is just 1. We have 10 more minutes. E to the 0 power is 1. What's the natural log of e? 1. And the reason would be since e to the 1th power is what? E to the 1th power is what? Remember, there's an implied base of e here. And when we do the around the world, we're doing this. It's real helpful to think of the around the world as well. E to the 1st power is e. Everyone agree? E to the 1st power is e. All right, let's squeeze this one in here. What would be the natural log of e squared?
That'd be
2.
Yeah.
What would be the natural log of e to the 10th? 10. In general, what's the natural log of e to the x? X. And of course, we could do it in the other order. What's e to the natural log of x? X. Because y equals e to the x, and y inverse equals the natural log of x are inverses of each other. Okay, that's what this means. So again, we can compose them in any order, and we get the answer. All right, let's try this example right here. What would be the natural log of 1 over e to the 3rd?
That'd be negative 3.
Negative 3. Yeah. Because e, the base e, which is implied e, the base e to the negative 3rd power, which is the log, which is the exponent, is 1 over e cubed. All right. So now we could do it in general for any base b. Not the common base, not the natural base, but any base b. What's log base b of 1 for any base that's legal? 0. And the reason would be is because b to the 0 equals 1. Of course, b can't be 0. What's log base b of b?
1.
1, because b to the first is equal to
1. Or B.
b, right. How about this? What's log base b of b to the 5th power?
5.
It'd be 5. Good. In general, on the next line, in general, what is log base b of b to the x?
That's X.
It's just x, right? Because how are log base b and y equals b related? Y equals b to the x, good. And y equals log base b of x are inverses. So that means we can actually compose them in any order, and we get back to where we started. So b raised to the log base b of x is also equal to x. I know it seems silly that we're doing those back to back, but it's no more silly than doing this. What's 5 times 1/5?
5.
5 times 1/5 is what? It's 1. How are 5 and 1/5 related to each other?
They're inverses.
They're multiplicative inverses of each other. Because when you multiply them together, they undo each other and you get the multiplicative identity, which is called 1. What if I do it the other way around? What if I do 1/5 times 5? It's still 1. That's the same idea. We're just composing them in different orders. We're logging it, and then we're exponentiating it. We're exponentiating, and then we're logging it. As long as it's the same base, they'll undo each other, and we're right back where we started. Got it? Okay. I'll say it's like this. All right, we're ready for example 2 now. Evaluate the following. What is log base 7 of 7 to the 3x squared plus 2th power?
3x squared plus 2.
3x squared plus 2. Boom. Got it? We start with 3x squared plus 2. We exponentiated base 7. And then we turn around and take that result, whatever it is, and we log it base 7. We're right back where we started with 3x squared plus 2. It's just the exponent, right? Since these are the same. All right. What is the natural log of e to the x? It's just x. Good. It's just x. What is 5 to the log base 5 of 5x? 5x. Yeah, 5x. What is e to the natural log of x?
X.
X, right? Because that's the same as e to the log base e of x, if you want to write it like that, which is just x. They undo each other. They're inverses of each other. What is log base 22 of 22 to the x? X. Y'all going to be ready for a quiz tomorrow. How about that on day 2? What about 57 to the log base 57 of x? It's just x. God, this is easy. This is easy. All right, let's see if we can get through example 3 and summarize, and we'll call it a day. Evaluate the following. Okay, so these are all numbers now. This is like in the beginning when I said it equals x, and I said let's evaluate it. It's just an expression. We're just simplifying. Log base 5 of 1 is equal to some number. What is it? 0. And the reason it's 0 is because 5 to what power is 1? 0. 5 to the 0 power is 1. All right. What's log base 1/2 of 1? 1/2 to what power is 1? Thank you.
0.
Go back to the previous example. 5 to what power is 1? 0. 1/2 to what power is 1? 0. Let's summarize. What is log base b of 1 for any legal base b? 0. That is the y-intercept of your log graph. If you have your log graph that looks like this, and it comes and does that, this is your y-intercept. It's at the point 1, 0.
So if it's log base something to 1, it's always 0.
Of 1. Of 1. It's always 0. Yeah. Because that base to the 0 power is the only way to get 1. All right. What's log base 12 of 12?
1.
1. Good. Good. What's log base b of b? 1. Excellent. What's the natural log of e? 1, because that's log base e of e, right? All right. What is log of 10? 1. All right, so here's the summary. This is what we need to walk away with today. Log base b of y equals x if and only if b to the x equals y. This is your conversion formula. This is the sentence structure, right? I go home and I do my math work, or I do my math work when I get home. It's just the same thing. You should be able to go back and forth between exponential and logs. Log base b of 1 equals 0. Log base b of b equals 1. Or in general, log base b of b to the x equals x. But that's also equal to b to the log base b of x because what special relation between these two?
The inverse.
Yeah. Log base b of x are inverses. So we can compose them in any order and get right back where we started. Okay. Hey, you do have enough information to start your homework tonight or this afternoon or whenever you want to. Yeah, I agree. Awesome. Any questions? All right. Have a merry festive rest of your day.